Doing okay? Our Thanksgiving break was okay?
So good.
So good? Oh, good to hear. I'm glad. Well, this is our last week 10, and then it's finals week, and then that's it. Maybe some of you I'll see next year, maybe not. We'll see. Our paths will probably cross if you're stats majors or something like that. Okay, so with our last week, I was trying to figure out exactly what we should cover. I feel like we've covered linear regression and multiple linear regression in fairly great depth, and a lot of it is cautionary tales of things, possibly misfitting your data. So I wanted to just kind of talk a little bit briefly on classification methods. So our last week we will cover classification methods, okay? And so I'm going to take a departure from our textbook. Our textbook actually does cover one a very good classification method, logistic regression, which we will cover today. Okay. I want to talk about linear discriminant analysis. Or LDA. And maybe we'll talk about k nearest to neighbors. Not today. Today will just be logistic regression. And I guess I should, I know the idea of, quote, kind of an aside, the idea of machine learning is like, I don't know, buzzword that people want to say that they're good at. Okay, so linear regression. Okay, so linear regression and multiple linear regression fits in this category of machine learning. These are supervised learning methods, okay? What we call supervised learning methods. In that we provide data. We also provide what the response is, okay? So we're giving it the x and we're telling it the y, and we're asking the computer or the machine to find a relationship or a pattern in the data that relates x to y, okay? So, we provide x and y, and we ask machine to find a relationship between x and y. Okay, and that's machine learning in its most basic form. Okay, and so linear regression, it's not as I don't know, trendy as maybe some of these more modern techniques, but it is tried and true, and it works. And it's very well understood. Okay, so logistic regression can be thought of as maybe an extension of linear regression, and even possibly multiple linear regression, in that we're relating x to a y, except the key here is that with logistic regression, y is not a numeric variable, y is categorical, and specifically for logistic regression, y is a binary categorical variable. Okay, so so today we will cover logistic regression. Okay, our response y is a categorical variable, and it's okay, and it will be a binary categorical variable, and so this this counts as a classification method. Okay, so is a classification method, and the way it works is that you know, we have inputs x, you know, x1, x2, x3, all the way to xp. Okay, and our output is a classification. 0 or 1. Okay, so examples include, you know, is it spam or real mail, which, to be cute, they might call it ham, or, you know, like will a you know, will a person default on his loans? You know, all sorts of questions like that. Okay, is this person going to do this or not? You know, is this person going to purchase a car? Maybe, maybe not. All right. So, so what we do is we relate x to the probability of y equaling 1. Okay, so we relate so in we relate x to the probability that y equals 1. Okay, and so this is what we have. Okay, and so when we look at data, okay, a lot of times your data is going to look something like this. Okay, so this is your data. You've got a 1 and you've got a 0, and let's say this is your x variable, and let's just say there's only one x here. Okay, so a lot of times you'll have data where, you know, so this could be something like maybe x is you know, a measure of let me think. So maybe x could be how I don't know, a measure of athletic ability. Okay, and so maybe this is like somebody scored, I don't know, there's some kind of physical fitness test and we scored people on how athletic they are. Okay, and then Y is 1 if they made the team and 0 if they did not make the team. So whatever team it is, right? So maybe it's a soccer team, who knows, okay? It doesn't matter, okay? And I don't know how athletic ability is measured, but let's say there was something, okay? And so what we'll often see is people with low athletic ability probably are all zeros, okay? Maybe there's a player whose athletic ability isn't super high, but still managed to make the team, okay? For whatever reason. Maybe it says this or that, whatever reason, okay? And then, and then you still might have some people who have high athletic ability, but maybe they didn't have the proper skills for soccer or whatever, and so they didn't make the team. Okay, so maybe it looks something like this. All right, so we want to find a relationship between X and Y. Okay, all right, so I'm going to just duplicate this this graph here. What's going on here? Okay. Okay, so linear regression. Okay, so if I applied linear regression, linear regression would just try to fit a straight line to this, right? And we would get something that looks something like that. Okay? And I think we can agree this is not a great model. Okay, so when we look at the residuals, we're going to see some major problems with it and things like that. Okay. But you could technically do linear regression and just kind of create a line at you could say if y if y is greater than y equal to 0.5, rather than using it to accurately model the data, you could just kind of say, if y is greater than 0.5, then we categorize it as 1, and y less than 0.5, we categorize it as 0. That this could work, okay? But yeah, the interpretability of the actual value of y itself is not going to be that great. Okay. So with logistic regression, we end up creating a different curve that looks like this, okay? And this curve, this is what we call a Oh, is this the logistic or the logit? I've got to look this up. I always get these mixed up in my head. One is vertical and the other one is, I think it's called the logistic curve. Let me just look up logit. Okay, so yeah, the logit's the vertical one. So the logistic is the, okay, so this is the logistic curve. All right, and what we have is that, so with linear regression, you would have y is equal to b0 plus b1x, right? And here, instead of taking b0 plus b1x directly, what we do is we say the probability that y equals 1 is going to be equal to e raised to b0 plus b1x divided by 1 plus e to the b0 plus b1x. Okay, so this is the relationship, and so what you can see is that here, let me copy this. You don't have to copy it again on your paper, but just okay. So what we see is that, when b0 plus b1x is very negative, okay, because b0 plus b1x is just a line, right? So when b0 plus b1x is very negative, then e raised to basically f of x plus 1 plus e to the f of x is going to be equal to 0 over 1 plus 0, which is 0. Okay, I shouldn't say is equal to, but is, very close to 0. Okay, and then when b0 plus b1x is very positive, then e to the f of x over 1 plus e to the f of x is going to be approximately infinity over 1 plus infinity, which is 1. Okay? And so what this does is it relates b0 plus b1x, which has a range of negative infinity to positive infinity, to a range of 0 and 1. Okay, and if we flip this around, oh, so you know what? Let me pause here and say a lot of my content for this week is going to come from the textbook Introduction to Statistical Learning with R. And this is the book. You'll if you take 101C, you'll cover all of these topics in greater detail also. And there's a section on, so you just type in ISLR. Okay, so here actually, just do Google search. Okay, and this book, Introduction to Statistical Learning with Applications in R. You can just you can download the book, and it will open up. And here I'm covering. So they're giving, this book is, I mean, you can buy it, but you can also get it free from the author's webpage. And I'm covering chapter 4 on classification. If you want, you can read chapter 3 for pleasure on linear regression, and this is a very good kind of condensed summary of pretty much everything we've done in this class already. And they actually even cover a little bit more in that they cover interaction effects, which we didn't really do, and all of this k-nearest neighbors. So this is a very good kind of compressed version of what we've done in our class. Doesn't really talk about diagnostics very much there, but it's still very good if you need a refresher. And then starting with chapter 4, we cover classification. Okay, and then so this is where we talk about logistic regression and all this. So a lot of today's content comes from that textbook. Okay, so anyway, so this is what we have. It looks like this, and then to you can kind of undo it and relate this back to you can the inverse transform would be the logit function. Okay. All right. So so running this in R. Okay. So because the relationship to x inside here is still a linear function, the logistic regression still falls under the category of a general linear model. Okay, so in R, all of our analysis has been with the LM object, okay, or LM function for linear model, and then you can create a general linear model, GLM, and that's how we try to fit data and estimate parameters in R. Okay. So okay, so so the function is just GLM, okay, and the key here for GLM is that we use what we call family binomial. Okay, so you're going to have basically y as a function of x somewhere in there. Okay, and then you're going to have family equal binomial. And so this makes it logistic. Data equals, whatever. All right, so we can try this out in R. Okay, the only problem is that interpreting the coefficients is now rather difficult. Okay, so you can there is a library that goes with the book, ISLR. Okay. And we're going to use the data default, okay? And so this is kind of how likely someone to default on their loans. Or credit card, I should say. Okay, so there's 10,000 customers. And to predict which customers will default on their credit card debt. So if you don't have a credit card, does everyone here have a credit card? Maybe, maybe not. Okay. So if you don't have one, you should apply for a credit card. You're a student, you're going to get terrible rates unless your parents did something to give you good credit, but you're not going to get. Your credit cards will not be very nice. You might have a $500 limit or a $1,000 limit, but sign up for one anyway. You don't have to use it, but just having an account open will start building your credit so that, after you graduate or, in a few years and you get a job and you want to buy a car or something like that, you'll have a score, and that will tell people that you are responsible, and if you borrow money, you will return the money. That's what it is, okay? And so it's to default on a credit card means that you did not pay your monthly payment, okay? So whenever you borrow money, you've got to pay it back. That's how borrowing works. And you've got to pay it back, and if you don't pay it back, the credit card company gets angry and they tell on you. They tell, there's these credit bureaus, and they keep track of if everybody has made their payments or not. It's like the Santa Claus. They know if you they keep a list of everyone, and if you don't do it, you get in trouble with the credit bureaus, and it stays on your record for 7 years. So if you miss one payment just for whatever reason, it stays on your record for 7 years, and that can harm your script. It will harm your credit score. So anyway, defaulting is a bad thing. Credit card companies don't want customers who default, because that means they're not getting their money back. And so anyway, we're looking at a bunch of data, and so here we're looking at, did they default? That's a yes or no variable, and we're going to look at the average balance of their credit card, and then also the income of the credit card. Okay, and so we just want to know how likely is someone to default based on the balance that they run. So we're going to create a model, and it's going to be GLM, and we want to relate default related to balance. All right, I guess I should plot this first. Okay, I'm going to write family equals binomial, and data is equal to default. But let me plot this. Plot, we want default and balance. data equals default. Oh, that is not. How do I do this? I just do balance and default. Oh, I see, as.integer. No, as.factor. Wait, as.factor. Darn it. Okay, wait, hang on. Structure default. So default is a factor. So let me see. Default, $ default, as.integer. Oh, ones and twos. Okay. Why is this not working? Balance is not in there. This isn't how it works. Man, life is hard. Okay, this is all of that, just for that. Okay, so this is what we have. This is, what would happen if I got rid of as.integer? Okay, yeah, it's exactly the same. All right, so this is what it looks like. Basically, those with low balances on their credit card, so most are under $2,000 or whatever, they didn't default, which is most customers, okay? And then, you know, these are the people who kind of borrowed a lot of money, and then they're like, I can't pay it. Okay, and so so these default. All right, so you know, if we fit a linear regression line, we would just get kind of this a flat line between these two things. We can ask for the summary of our model. Okay, and it spits this out. Okay, and it says, you know, both the intercept and the balance are very significant, but you know, we got these stars here, but what do these estimates mean? Okay, so we have to keep in mind that the function that we have here is in the form y is, so let me just kind of like an intermediate form. We've got an f of x, which is in the form b0 plus b1x, okay? And then the probability is equal to e raised to the f of x divided by 1 plus e raised to the f of x, okay? So I can take our model $ coefficients, okay, and I can get both of these. So that's our intercept coefficient and our slope coefficient, and I can put these into things, okay, and then so I can create a function of x that evaluates this, and this will be intercept plus slope times x, right? Okay, and so now I can create a my x, which will be a sequence, and we'll go from 0 to 2500, and then so our f of x, I'm going to just call it fx, is going to be f evaluated at x. So far so good. So all I'm doing is just evaluating all of my x's at f of x, and then we're going to turn this into the logit. So our y will now be e raised to the f of x divided by 1 plus e raised to the f of x. Oops, it's not e, I have to do exp, so sorry. In R, it's not e, it's exp. Okay. Rats. On my graph, it's not 0 and 1, it's 1 and 2. So let me, what should I do? I should subtract 1 and 1 from everything here, huh? Can I do that? No. It hated that. It got mad at me. As dot integer this. Okay, so there we go, 0 and 1. All right, and so we'll try this. I hope this works. We can do lines x, y, color equals red. And there you go. There is our logistic regression line, okay? And you're like, why isn't it way up here? It's because it's hard to see, but there's still a lot more people who are paying their bills and not defaulting. So even if you're right here at 2,000, 1,700 or whatever, there are more people who are paying, and so the probability of default is still less than 0.5. But right around 2,000 or whatever, then you become a higher risk for defaulting or something like that. Is that okay? All right, so that is kind of, so the interpretation of all of this. Yeah, what does this mean? Well, so we can, so the interpretations of the coefficients are kind of tricky, right? Our intercept is negative 1.065, or basically negative 10, and our balance is 0.0055. Yeah, there's no direct there's not really an explanation for the interpretation as a direct relationship to probability. However, I can do x1, let's say, is 1,000, and x2 is 1,500, and we'll say x3 is 2,000. Okay, and I can find fx of x1. We'll call this y1, and I'll do the same for y2, y3, and y4. So we can talk about how these things change. Oh, no. Sorry, I have to do this. This is not correct. Sorry. Okay. I'll post all this. F of x1. Okay. So now I'm just calculating the probability based on x1, x2, and x3. Okay, so y1, when you have $1,000 in debt, the probability of default is 0.005. So it's less than 1%. At 1,500 in debt, it's oh, I'm like, that's not right. You got you're now an 8% risk, and at 2,000 you are now a kind of a 60% risk. Okay, so we can talk about kind of the change in kind of probabilities, and we can talk about log odds. Okay, but as far as direct interpretation goes, it's less wrong wiki. I don't want the less wrong wiki. Yeah, I don't even know what that is. This is not what I'm looking for. But we can talk about the change in probabilities as x1 and x2 and x3 change, okay, or as your x's change. However, kind of looking at the coefficients in of themselves will not offer very much intuitive understanding of what is happening in the equation, okay? But if and in the same way, we can expand logistic regression to be to multiple logistic regression, in that rather than just b0 plus b1x, you can have b0 plus b1x plus b2 x2, and you can expand this. You can include more x terms because essentially you're just predicting, you're creating a linear model here, and then you're relating the linear model to your categorical via the logistic function. Okay, so I'll write that. Okay, so logistic regression can be generalized to a, you know, multiple variable form, and you have you create a new f of x b0 plus b1 x1 plus b2 x2 plus all the way to your p variables, okay, and then it's now probability of y equal to 1 is related still via the logistic relationship. Okay, so the chapter 8 in the textbook we've been using so far goes, you know, into kind of a bit more rigor in the coverage of this topic. I think just a kind of a high-level overview at this point is acceptable for logistic regression, and then we'll also just briefly touch on try to touch on linear discriminant analysis, which allows for multiple categories. We'll talk about that on Wednesday. Okay, so we'll end there, and we'll see you guys in a little bit. I don't know if you guys got my email, but no office hours today, so hope that's okay. All right, we'll see ya.